I didn't need a second glance at the spectrum. What James Webb had uncovered was already rewriting the rules I had spent my entire career teaching. The moment the data for the object now called Canucks LRDZ 8.6 reached my desk, I realized we were staring at something that had no business existing so early in cosmic history. 600 million years after the Big Bang is simply too soon for a galaxy this compact to be harboring a monster of a supermassive black hole. Yet the evidence was undeniable. The light was faint, stretched, and reddened by cosmological expansion, but its signature spoke with reckless clarity. This was a predator in the infant universe, devouring matter with a kind of hunger that mocked our theoretical timelines. James Webb's discovery of the little red dots had already unsettled many comfortable assumptions in cosmology. But this one, this violently luminous speck, was different. It was the outlier among outliers, a cosmic rebel, refusing to obey any prediction we have about how galaxies and black holes grow together. And that is why I couldn't ignore it. That is why I am speaking directly to you now. Because when nature violates your expectations, you do not excuse it, you follow the trail of truth wherever it leads. The redshift alone told us the age. At z equals 8.6, we are looking more than 13 billion years into the past, back to when the first galaxies barely had time to assemble the simplest stars. The early universe should have been too chaotic, too metal-poor, too energetically violent for a well-fed supermassive black hole to sit calmly at the center of such a fragile structure. And yet the quasar-like spectrum said otherwise. Strong ionization lines, rapid gas rotation, a gravitational engine pulling matter inward at a rate that pushed against the limits of physics as we know them. I studied the data again and again, searching for any alternative explanation. Maybe a starburst, maybe an extreme supernova remnant, maybe gravitational lensing amplifying something less dramatic. None of it worked. The pattern of radiation was too clean, too organized, too sharp. Accretion was the only answer. Rapid, violent accretion from a black hole so massive it should have required hundreds of millions more years than it actually had. For decades we operated under the principle of co-evolution, that galaxies and the black holes at their centers grow side by side, each influencing the other in a kind of cosmic duet. But what happens when the duet turns into a solo performance? What happens when the black hole races ahead, dwarfing the galaxy that is supposed to be its host? In Canucks LRDZ 8.6, the black hole is not simply oversized, it is grotesquely oversized, larger than the stellar mass of the galaxy itself. It's as if a newborn child were carrying the weight of an adult titan inside its chest. This forces a question few are comfortable asking. Could supermassive black holes have been born big, not grown big, born big? Seeds not forged from collapsing stars, but from entire clouds of primordial gas giving up their stability and collapsing directly into mammoth black holes in a single catastrophic plunge. That scenario has long been a fringe possibility, invoked only when our models felt particularly inadequate. But now, suddenly it is no longer a theoretical toy model. Suddenly it stands as one of the only viable explanations for what James Webb has placed before us. There is no gentle way to say it. Our understanding of the early universe is incomplete. The discovery of Canucks LRDZ 8.6 is not an adjustment on the margins. It is a strike at the very framework of how we believe structure forms. And in this business, when the framework cracks, the only honest response is to rebuild it. The more I examined the spectrum, the more the evidence cornered me. This black hole was not just active, it was ravenous. The gas surrounding it was moving at extraordinary velocities, whipping around the gravitational well as if caught in a storm with no horizon. Strong ionization lines carved themselves into the spectrum like scars. Oxygen, hydrogen, and neon signatures blasted by an energy source far too concentrated to come from star formation alone. I've analyzed countless accretion disks throughout my career, but this one carried a restless, almost feral intensity. The early universe was supposed to be a cosmic toddler, barely learning to form stable stars, yet here was a fully fledged monster, already burning through its surroundings with the confidence of something ancient. The sheer imbalance between the black hole's mass and the mass of its host galaxy was what disturbed me most. In typical galaxies, the central black hole is a footnote, small, influential, but always proportionally tied to the growth of the stellar population around it. But in this object, the ratio was flipped. The black hole was the main structure. The galaxy was the footnote. The stars looked like an afterthought, a thin scattering of light wrapped around a gravitational core that had no patience for the slow choreography of cosmic evolution. I tried to imagine the physical conditions that could produce such a mismatch. What kind of environment allows a black hole to balloon so quickly while the galaxy barely forms a coherent structure around it? Traditional models crumble under this question. They depend on gradualism, small seeds, long growth, steady feeding. But the universe, as James Webb keeps reminding us, is not obligated to follow our intellectual preferences. If anything, the early cosmos may have been shaped by episodes of violence so intense that our equations cannot yet account for them. Direct collapse black holes, once dismissed as niche theoretical exotica, suddenly appear not only plausible but necessary. Imagine a gigantic cloud of pristine hydrogen, untouched by metals, unpolluted by previous generations of stars, collapsing under its own weight. No turbulence, no fragmentation, no time for stars to form first, just a catastrophic plunge into darkness, birthing a black hole with a mass tens of thousands, even millions, of times the mass of the sun in one go. When I brought this possibility to colleagues, their reactions split. Some were intrigued, others were uncomfortable, a few outright resistant. The idea that supermassive black holes might precede galaxies rather than follow them reshuffles the hierarchy we have built into our cosmological narratives. We prefer stories with order, with symmetry, but the universe has no obligation to be polite. It unfolds through whatever mechanisms reality permits, not through the stories we find aesthetically satisfying. There is another unsettling question. What fueled the growth of this black hole so quickly? Even with an oversized seed, even with direct collapse, you still need a steady supply of matter to sustain such explosive early accretion. And the early universe was not generous. It was chaotic, expanding rapidly, pulling matter apart as often as it brought it together. For Cannock's LRDZ 8.6 to feed this efficiently, something must have funneled gas into the center with remarkable consistency. A dense inflow channel, a primordial filament of cold gas, a gravitational funnel created by early dark matter structures. None of these are impossible, but none are established either. Yet the observational truth remains, this black hole did grow. This galaxy did host it, and the universe did allow this anomaly to exist in a time when such stability should have been impossible. Every time I look at the data, I feel less like a scientist confirming a result and more like an archaeologist brushing dust off a buried contradiction, something left behind by a universe that evolved far faster, far more aggressively than our textbooks ever predicted. If this is the rule and not the exception, then everything about our understanding of cosmic dawn must be rewritten. The more I confronted this anomaly, the clearer it became that Cannock's LRDZ 8.6 was not simply misbehaving, it was exposing the cracks in the foundation of our cosmological understanding. For decades, we have leaned comfortably on the idea that galaxies and their central black holes rise together step by step like dancers locked in a synchronized routine. But this object stands alone on the stage, moving out of rhythm, accelerating long before the music should have even started. It forces us to confront a possibility we've tried to avoid. Perhaps supermassive black holes didn't wait for galaxies. Perhaps they rushed ahead, setting the pace, dictating the formation of everything around them. The assumption of coevolution collapses when the black hole outweighs the entire stellar mass of its host. This is not a subtle deviation, it's a cosmic rebellion. You cannot claim a duet when one voice is drowning out the orchestra. And if this is not an isolated case, as early hints from JWST suggest, then our entire model of galaxy formation becomes a story told out of order. We have been reading the middle chapter without knowing that the prologue was missing. What truly unsettles me is how this discovery reshapes the question of origin, not just growth. How big were the first black hole seeds? If they came from the collapse of massive early generation stars, population 3 stars, then they would start with perhaps 100 solar masses, maybe 1,000 in optimistic scenarios. But that is nowhere near enough for what we observe here. There is no path, no timeline, no accretion rate that takes a seed of a few hundred solar masses and inflates it into a billion solar mass monster in the mere blink of cosmic time. So we are forced to consider a bolder possibility: seeds born enormous, bypassing the stellar stage entirely, direct collapse black holes, a collapse not of a single star, but of entire clouds, vast pristine reservoirs of hydrogen collapsing as a whole, never forming stars because the gas never fragments, a monolithic implosion, a gravitational catastrophe birthing a giant in a single act. Many physicists resist this idea because it sounds too extreme, too dramatic, but the universe at that time was extreme. It was dramatic. It was nothing like the universe we observe now. Our instincts, shaped by the calmness of the present-day cosmos, are not trustworthy guides to the chaotic physics of cosmic dawn. Even if we accept direct collapse, we still confront another dilemma. How did such a seed continue to grow in a universe expanding with ruthless speed? Feeding a black hole requires a stable stream of matter spiraling inward. But in the first few 100 million years, the universe was tearing itself open, stretching space between objects, pushing matter outward. Any feeding mechanism operating under those conditions had to be exceptionally efficient, far more efficient than anything we've confirmed observationally. Something, whether a cold gas filament, a dark matter halo, or an early gravitational funnel, must have acted as a cosmic conveyor belt, channeling material straight into the maw of this newborn monster. Yet even this still feels incomplete. The magnitude of the growth challenges not only astrophysics, but cosmology itself. It suggests that the early universe may have contained pockets of density far higher than our models predict. Regions where matter piled up more quickly, where collapse happened more readily, where gravitational structures formed at breakneck speed. If these pockets were common, then the early cosmos may have been far more clumpy, far more uneven, and far more conducive to rapid runaway collapse than we imagined. These questions do not simply stretch the theory, they rupture it. They call into doubt our assumptions about how the first stars lit up, how the first galaxies assembled, how dark matter sculpted the scaffolding of the cosmos. If supermassive black holes formed early and grew explosively, then they may have influenced the entire architecture of the universe, shaping the formation of galaxies through their radiation, winds, and jets long before galaxies reached maturity. Every time I revisit the numbers, I'm struck by how little room they leave for comfort. This isn't a matter of adjusting parameters on a model or refining a simulation. It is a matter of returning to the drawing board. The discovery of Canucks LRDZ 8.6 demands a new chapter in cosmology, one where black holes are not byproducts of galaxy formation, but active protagonists in the earliest scenes of the universe. And I find myself asking a question I never thought I would confront so directly. What if we have been telling the origin story of the universe backward? The scientific weight of this discovery extends far beyond curiosity. It forces us to confront the architecture of the cosmos itself. When a single object violates your models, you call it an anomaly. But when multiple observations begin echoing the same pattern, when more little red dots exhibit overmassive black holes, you face a shift in the paradigm. Canucks LRDZ 8.6 is not simply a rebellious data point, it is a herald, a signal that everything we believe about the first billion years of cosmic evolution is incomplete. And that realization carries profound implications for every branch of astrophysics. The fact that this galaxy was documented in a peer-reviewed study published in Nature Communications gives it a scientific weight that cannot be dismissed. The analysis was meticulous. The red shift was measured with precision. The accretion signatures were clearly defined. Yet what gives this discovery even greater significance is not the confidence in the data, it's the disruption it introduces. Scientific progress thrives on disruption, and this one is seismic. The logical response is to expand the search. If the universe hid one such object, it can hide many. James Webb is powerful, but even Webb's extraordinary sensitivity represents only a fraction of what lies beyond our observational horizon. The early universe is a vast, dimly lit frontier where most light has been stretched into wavelengths too faint or too long for current instruments. The fact that Webb captured CANUCS-LRD-Z 8.6 so cleanly suggests that similar galaxies are not rare. They are simply faint, and our tools are only now sharp enough to expose them. I expect the catalog of overmassive black holes to grow steadily over the coming years, and each new discovery will peel back more layers from the murky origin of structure. But Webb alone is not enough. The next step requires a symphony of instruments working together. ALMA, the Atacama Large Millimeter Charge Submillimeter Array, offers the unique ability to track cold gas, the raw material fueling black hole growth. While Webb reveals the ionized regions and the spectral fingerprints of accretion, ALMA can map the reservoirs feeding these beasts. It can show us whether the gas is flowing in smooth streams, chaotic bursts, or structured filaments tied to the cosmic web. Pairing Webb's infrared eye with ALMA's millimeter precision transforms these distant galaxies from static images into dynamic systems. It lets us track their evolution, infer their histories, and predict their fates. This combined approach holds the key to determining whether CANUCS LRDZ 8.6 is an exception or the first member of a new class of primordial objects. If multiple galaxies show black holes outweighing their hosts at such early times, the entire theory of coevolution collapses. The black hole becomes the architect, not the tenant. It shapes the galaxy from the inside out, forcing us to rethink feedback mechanisms, star formation rates, and the stability of early cosmic structures. The implications ripple outward into cosmology itself. If black holes formed early and grew explosively, they would influence the thermal history of the universe. Their radiation would ionize gas, alter the timing of reionization, and affect how quickly matter clumped together. They would serve as gravitational anchors, accelerating the formation of proto-galaxies, possibly even seeding the large-scale structure we map today. In other words, the role of black holes may not have been passive. They may have been engineers carving pathways through the young universe. And then there's the philosophical shift. Science is driven not just by what we see, but by the questions those observations force us to ask. CANUCS LRDZ 8.6 asks whether we have misunderstood the power hierarchy of cosmic evolution. We assumed black holes needed galaxies, but perhaps galaxies needed black holes. Perhaps the gravitational and radiative influence of these giants provided the scaffolding, stability, and pressure needed for star formation to ignite. These are not small revisions. These are not mild corrections. These are paradigm-level transformations. Discoveries like this reshape disciplines, rewrite textbooks, and refine the questions future generations of scientists will ask. The roadmap ahead is clear. Observe more, model deeper, simulate faster, question louder. We are standing at the threshold of a new era in cosmic archaeology, one where the shadows of the first black holes reveal the blueprint of the universe itself. What CANUCS LRDZ 8.6 ultimately forces upon us is the recognition that supermassive black holes do not require billions of years to rise to prominence. They can emerge abruptly, erupting into existence with masses large enough to dominate their surroundings almost instantly by cosmic standards. This realization reshapes the tempo of the early universe from a slow, gradual unfolding to something far more dynamic, an environment where structures appear suddenly, violently, and with consequences that cascade across billions of years. The discovery tells us that the cosmos did not start with a whisper. It started with a surge. Every line in the spectrum, every turbulent swirl of gas, every gravitational imprint carved into the starlight of this distant object points toward a universe more impatient than we imagined. A universe capable of forging giants in the blink of an eye. As a physicist, I am trained to appreciate elegance, but the early cosmos was not elegant. It was raw, explosive, and unrestrained. And within that chaos, it seems nature found a shortcut, forming black holes that were not seedlings, but saplings already towering over the forest they fell into. This does not diminish our understanding, it enriches it. For years, we framed cosmic evolution as a slow climb, with galaxies gradually nurturing their central black holes through steady feeding. But the evidence now points toward an inverted sequence, one where the black holes emerge first and galaxies scramble to form around them. This inversion transforms our models from being galaxy-centered to gravity-centered, with black holes acting as primary engines rather than secondary outcomes. It forces us to rewrite the opening chapters of the universe, placing supermassive black holes not as supporting characters, but as protagonists. And that shift carries profound implications for the questions we ask next. If these giants formed rapidly, what governed their birth? Was it the collapse of pristine hydrogen clouds, as the direct collapse model suggests? Was it driven by rare pockets of extreme density seeded shortly after inflation? Or does an even deeper mechanism operate beneath our understanding, one tied to the nature of dark matter, quantum gravity, or physics that has not yet emerged from theory into measurement? We are only beginning to scratch the surface. James Webb has opened a new window, but behind that window lies a landscape still obscured by distance and time. Each new detection pushes us further back toward the moment when the first structures crystallized out of chaos. Each anomaly reminds us that the cosmos does not follow our expectations. It reveals them to be incomplete. What excites me most is not the disruption, but the invitation. The universe is offering us clues, daring us to question more deeply, to imagine more boldly, to abandon the comfort of old frameworks, and build new ones grounded in evidence that defies prediction. That is how science advances, not by defending tradition, but by confronting contradiction. As we continue to study objects like Canach's LRD Z 8.6 with Webb and ALMA, as computational models grow more sophisticated, and as theoretical frameworks widen to incorporate more extreme possibilities, the picture of cosmic dawn will sharpen. And when it does, I believe we will find that the growth of early supermassive black holes is not an anomaly. It is the key, the blueprint, the missing chapter that explains how the largest structures in the universe emerge so quickly. The story of the cosmos has always been one of emergence, but perhaps we misunderstood the scale of that emergence. These early black holes may have been born in flashes of gravitational violence, shaping everything in their wake. And as we decode their origins, we are not merely learning about the past, we are learning about the forces that still shape us today. The universe keeps its secrets well, but with every new discovery, it loosens its grip just a little. And with that loosening, we inch closer to understanding the truth that in the beginning, darkness did not wait. It arrived fully formed, burning with a hunger that helped light the universe itself.